Hi. We're going to be today using maths to try and cluster crystals together and separate them apart based on if they're actually similar or not. And we'll jump right into it with a model for crystals, which should be pretty familiar to everyone. There's nothing too much new here yet. So we take a crystal and model it like this as a periodic set, which to a mathematician is a basis, or these vectors here, which define the unit cell. So usually they're given as your cell parameters, but as a mathematician, we'd call it a basis. And then you take a finite set of points inside the unit cell, which is the motif. So these points will be in the centers of atoms for us. And then obviously the points repeat infinitely in all directions according to the basis to generate this infinite set of points, which we call the periodic set. And we chuck away the atomic types and their bonds. I know people like those, but you can keep them aside as labels for your points and labels between your points, but we're actually not going to use them for our classifications. So this is the starting definition. Let's talk about when things are the same and when they're not. And for us, this means isometry. So as a rigid object, crystal is studied really up to rigid motion. If you apply a rotation or a translation to your crystal, it doesn't change what it is, to your periodic set, I should say. And so those two things should be considered equivalent. By those two things, I mean, if you can get one periodic set from another via a rigid motion, they should be considered the same thing. And for math's sake, we include reflections in this, which a little bit difficult, but basically an isometry also includes reflections, and that's a much easier class of transformations to study, so we'll include them. So everything which is isometric to anything else is equivalent, and this is what we call a crystal in our work. A crystal is this infinite class of periodic sets, a periodic set being a motif and cell pair, which are all equivalent to each other up to some isometry. So this is the start of the sort of ambiguity problem that we're going to face. And here's some sort of toy examples of ambiguity in a representation with a cell and a motif. Even so, these three up top, I think a lot of people have seen them, but if you haven't, then sometimes this even confuses people who are familiar with crystals, but they all define the exact same set of points up to isometry. If you remove the lines defining the unit cell, we've just chosen different input representations to generate the same thing. And even if we fix the unit cell, like in this example below, we can just move it around on top of this periodic set in the middle and get a bunch of different motifs. So anything that depends on a unit cell or depends strictly on the motif is not really going to work for classifying and distinguishing periodic sets. And here's a real example. We'll see a bit more from this data set later. So this is a CSP run on a molecule we call T2, which is this tripod type thing, which we'll see in a bit. And it can form this hexagonal crystal. And in the CSP run, there's about 7,000 crystals in this data set. Here's an example of 3, where it's approximated the same crystal 3 times with very different unit cells and motifs. So we want some way of being able to put these 3 in the same group and distinguish them from everything else. So we'll talk about more strictly about what how we can sort of take these infinite classes of periodic sets we call a crystal and find if 2 things are in the same class or if they're in different ones. So the easiest thing to have would just be a function where you could put in 2 periodic sets and it would tell you, is there an isometry between them, yes or no? But unfortunately, that doesn't exist. It's a non-starter, so we can take a different direction and use an isometry invariant. So an isometry invariant is something where you calculate something from your periodic set, and that won't change if you choose any equivalent representation of that periodic set. So I think a good intuitive example is density. So you can think of density like a chemist, or we should be thinking about point density, since we've thrown away the atomic types, the number of points per unit area or per unit volume. If you apply an isometry to a crystal, that isn't going to change. But that means that if you have two different crystals and you compute their densities and they're different, then you can use that to infer that the crystals you started off with were different, or there wasn't an isometry between them. So we're going to use an invariant, an isometry invariant, to tackle this problem. And I mentioned briefly the reduced cell, which is another invariant. So you can apply an algorithm to find this a reduced cell, which is the same no matter which input cell you started with, as long as the periodic sets you started with were literally isometric. But we don't just want invariants, because it's not quite enough for what we like. The problem with, say, a reduced cell is discontinuity. So in this sort of toy example, we double the unit cell and apply a small perturbation, and the reduced cell discontinuously doubles. So we get a very, very different reduced cell for these very similar periodic sets as input. This is reflected in these examples as well, because these three things aren't literally isometric. There's a slight bit of noise between them. And that means that if you reduce the unit cell, you probably won't get the same thing anyway. So continuity we want because of noise, because of floating point and rounding errors. Even simulated crystals are subject to this sort of thing. So it can't be we want exactness in terms of isometric invariance, but we also want to continuously quantify similarity. We don't want big changes when we smoothly move around points. So this is sort of the problem statement that we're going to solve in all the slides after this, hopefully, to some extent. We want a map from periodic sets to some numbery thing with these properties. So invariance we've gone over. If you put two things which are isometric through this map, you'll get the same thing on the other side. Continuity, meaning that if we perturb points by a small amount, then the output of this will only change by a small amount. So we should see a small distance between similar crystals. And then the third point here, probably the hardest to talk about in relation to our invariance, but it's important to note, is completeness, which means it distinguishes different things. And that's the problem we have with something like density. Density is nice, you can plot it on one axis, so you get all the crystals on sort of one dimension, but it's not very distinguishing for data sets of any decent size. You can find two different crystals that have the same density, just happen to have the same density, because they can only take on values in a small range. So we want it to be a bit more distinguishing than that. So with the problem statement, we can move on to start defining our solution to this, our invariant. And I'm going to use a toy example of finite sets, but then we'll just extend it to the case with crystals. So these two sets are kind of interesting because they're obviously different. They can't be mapped onto each other with an isometry. But if you list the distances between all the points, just in order, between all points and every other point, then you get the same list. And that's actually one descriptor that people use with finite sets and with crystals, is the set of distances between all points in the set, or motif. But these two can't be distinguished by that. So let's try and construct something a bit better. And this is where we start. So this is step one, to construct the pointwise distance distribution. And here I'll state it for a finite set, but then later we're going to extend it. So we construct this this matrix over here from our set. Each point in the set gets one row. So for each of these 4-point sets, we end up with 4 rows. And in a row, it just lists the distances to points in order. So say this point here has mapped to this top row. I don't know if you can see my cursor, hopefully. And its nearest neighbor is root 2 away. So that's the first. Its next is 2 away, and the next is root 10 away. So we just list those 3 distances in order. And we end up with 4 rows, 1 for each point, 3 columns, because each point has 3 neighbors. And we do that for both. So this is our sort of step 1, quite a simple construction. But the idea is, instead of putting all the interpoint distances into one list, this is going to store some like relative information about distances between different points. So there's a few problems with this matrix as it stands. The first is that we need to order the rows, because if I had just chosen to order my points differently, then the rows of this matrix will all just be reordered some other way. So in order to remove dependency on the orders of your points, we have to order the rows of these matrices, and we do that lexicographically, like in a dictionary. So the smallest leftmost element goes first, and then the next row, but it's a stable ordering, which will be the same no matter which order you chose for the input points. And then after we've done that, there's one more step. So here is here's the PDDs of the set. After we've ordered the rows, we're going to collapse identical rows. So this doesn't do so much for finite sets, but it'll be important in the crystal case. So after we've reordered the rows, we look at if any rows are identical, and if we are, we merge them into one and give weights proportional to the number of appearances. So here, for this trapezium, if we look back at what we got 2 set pairs of identical rows. So they ended up as just 2 rows, each with a weight 1/2, as opposed to this kite shape, where we had 1 pair of rows which was identical, but the other 2 were unique. So they didn't get collapsed into each other, and we have these weights. And we end up with 2 unequal matrices. These are the pointwise distance distributions of the sets. And these are isometry invariants, which are continuous. So one thing to note before the next slide, where we have an actual crystal for once, is that the reason that rows collapsed is because there were symmetries. This trapezium on the left, we have a mirror symmetry vertically in the middle, and it maps these 2 points onto each other and the bottom 2 onto each other. And so they're symmetrically equivalent, and their nearest neighbor distances are all the same. So that's why we ended up with 2 unique rows. Whereas here, the symmetry is through the middle, and 2 of the points are invariant under that symmetry. So they have unique lists of distances to neighbors. Whereas these 2 points are symmetrically identical, so they have the same list, and that got collapsed. So, I have also mentioned our paper here, with the more technical sort of definition, also for periodic crystals, which looks like this. So I've taken our friend from earlier, this hexagonal thing. I think there are 2 molecules in this unit cell, so 46 atoms in a molecule for 92 points in this unit cell. And now each point in the unit cell is going to have 1 row. Since we now have an infinite set of points, we don't do a row for every point, we do a row just for points in the motif. And this is where the collapsing comes in handy, because if you double the unit cell, we're going to end up with double the number of rows because we've doubled the number of motif points. But if you collapse them back down, then you receive the original matrix, which you get with this reduced unit cell. And in the same way that rows collapsed before because of symmetries, we get the same scenario here, where collapsing the rows gave us 1 row for each atom in the asymmetric unit. So I've shown the molecule on the left here. It's this tripod thing with 3 arms, and then the asymmetric unit is 1/2 of one of those arms. And in the end, we got 10 rows, 1 for each atom, and the weights here correspond to the Wyckoff multiplicities of the atoms, so the number of unique sites they generate when you apply all the symmetries. And this is actually quite nice because it gives us a way to go in the other direction. We can do a shortcut. Instead of doing distances to all motif points, if we already know the asymmetric unit, we'll just do it for the asymmetric unit, and then we can figure out what the weights would have been anyway. So this is what the pointwise distance distribution of a crystal would look like. I think these are actually the values for this actual crystal, and I've probably gone up to about 100 rows, 100 columns. So I should mention that in the finite case, the number of columns was 3 because there were only 4 points. But now we have infinitely many points to measure distances to. We just have to choose some cutoff value. And I think here I chose 100, which is pretty typical for us. So an atom's 100th nearest neighbor is going to be around 9 angstroms away. So this pointwise distance distribution, importantly, is an isometric invariant. So if you choose any isometrically equivalent representation of this, you'll get the exact same output. But it's also continuous under perturbation. Even if you double a unit cell and apply a perturbation so it's not reduced, we'll see that because of the metric we choose between these, we actually still get continuity. So this is the Earth mover's distance. So the Earth mover's distance is good because we can compare these PDDs which have different numbers of rows with weights. And you can imagine, I think I showed earlier, the case where we extend the unit cell, apply a small perturbation. Now we have double the number of rows. So we need some way of accounting for that and keeping our continuity. So what Earth mover's distance does is it takes 2 PDDs and compares the rows in one to the rows in the other, creating this sort of cost matrix between the rows. So for this finite case, a 2-row PDD and a 3-row PDD ended up with a 2x3 cost matrix. And the weights sort of carry over to the rows and columns. Then Earth mover's distance basically finds the ideal flows between the rows and the columns, or it finds the cost of moving one distribution of rows into the other. And it does all this while respecting the weights, which is important because, again, if you do this thing of doubling the unit cell, we end up with twice as many rows in the PDD, but the weights all half as much. So when we compute this distance matrix, even though it's twice as long in one direction, the flows still all work out proportionally because the weights are all respected by Earth mover's distance. So everything is accounted for with continuity. And this is the formal statement here. This distance dB is bottleneck distance, which means that if I take if I take one periodic set and apply a perturbation, say I move, no point moves more than epsilon, then the bottleneck distance is epsilon or something like that. So it's the maximum distance that any point moves under a perturbation. And we know that the Earth mover's distance is at least is smaller than 2 times this distance between sets. So that's formal continuity there. And I'll also introduce the simpler but related average minimum distance, which can be computed from the pointwise distance distribution. We just take a weighted average over the columns and we end up with a single vector, which is also very nice and distinguishing for sets, although it's a little bit less strong and you don't have one row for each point in the original set. You have just one vector summarizing the whole thing. And these are much faster to compare with. So it acts as a nice filter for a check for isometry, especially considering this result down here. So let's quickly go over the results that we have for this. So probably the main selling point of these things is they're very fast comparison tools, faster than most of the ones that exist right now, but they're also quite distinguishing, unlike something like density. So we managed to compare many crystals from the CSD. There's a large chunk that don't sort of work, but most of them do. And we managed to find 5 isometrically identical ones. Actually, they had the exact same list of motif points, but what we ruled out is that there are no other isometrically identical crystals with different compositions, which shouldn't happen. A bad actor could say rotate a crystal, re-upload it with a slightly different composition, and nobody would be any the wiser. But we've ruled this out. And then recently we managed to use this, but instead of putting a point in the center of each atom, we could just point in the center of each molecule. And this is good for comparing two structures with different molecules, because if you have different molecules, similarly to, say, packing similarity, if we give them to PDD, it's just going to say they're very different, because different molecules, it's obviously it's a different structure, it just is. But what we could see is that these molecules, one was T2, the tripod molecule, and the other one was similarly shaped, but they packed in similar ways. So we were able to put points in the center of the molecules and see an analogy between two landscapes. And here's a quick picture of the data set I mentioned earlier, the CSP run T2, which found 5 experimental crystals. These are the actually synthesized ones out of the 7,000 or so. And this is a minimum spanning tree containing all the crystals. I think it's colored by energy. So these dark spots are where there are energy dips. And the idea is basically that this tree is constructed using our distances. So things that are similar, according to us, should live in these bubbles. And we find that the same crystals repeated many times for all of them, but we managed to put them all together. So a summary, because I think I may have run over. We defined what a crystal is rigorously and mathematically, and then shown that our tools actually are well defined on that definition. As we wanted, continuous isometry invariants, and distinguish things quite well. And if you want to try this stuff on your own SIFs or whatever, then here's a link to the repo.
You're absolutely fine on time, Daniel, actually. Anything slightly under. So there you are.
Right.
But so we do have some time for questions, if anyone has any. I'd feel guilty asking a question here, as I've kind of co-supervised Daniel, but I will do if needs be. Yeah, round of applause. So has anyone got any questions for Daniel? No? Okay. Well, I'm going to ask a technical question. So when you collapse the PDDs, how do you define equal? So what do we define as the when two distances or two vectors are actually equal? Because I mean, obviously with small perturbations to crystal structures, that presumably can have quite an impact.
Yeah. So well, theoretically, they have to be literally identical.
Right.
But in practice, we actually don't do that. We collapse within a kind of tolerance. When we collapse is when all elements of two rows are within, I think, 1 times 10 to the minus 3 or 1 times 10 to the minus 4. Either, I think I might have chosen the same as the sort of tolerance that for equivalent sites that the CCDC uses.
Right.
Because real crystal, if you get a real crystal, even the rounding point, the floating point errors will mean that two rows might not be collapsed just because they're not literally identical. So we have a little bit of tolerance in collapsing rows, but not much.
We could actually use the genuine uncertainty on the distance. Actually, I think that might be an interesting thing to explore.
We've avoided using that for a long time because we don't like it, but I think it'll have to come into it at some point. Yeah, you certainly could involve those somehow.
Yeah, indeed. Anyway, Simon's got a question. Do you want to unmute yourself, Simon?
Yes, thank you. That's a very interesting talk. And I don't know that I've got it entirely yet. I think I'd need to try your this code on the GitHub. But how much does it matter how big the structure is? From your description, it sounds like the size of the structures that you're wanting to compare isn't really an issue. Is that correct? By
size of structure, do you mean number of motif atoms? Points?
Yeah.
Number of atoms in a motif?
In a unit cell, yeah.
It doesn't matter really. You can compare anything of any size with anything else, and it treats it kind of objectively as a set without a unit cell, totally independent.
Right. I wonder, do you? You're comparing all the time the actual structures, aren't you? Have you ever thought of I don't know whether this would be useful at all, but looking at the looking at what we refer to as Patterson, as a, kind of the Patterson function, a vector map, in other words. So your points aren't the atoms themselves, but the vectors between them. This formed an early method for solving crystal structures, but it can be useful for detecting situations where you have quite similar where you've missed translational symmetry. So what you see if you've got in the example that you showed initially of that kind of hexagonal cell, all the cells were the same, but you had slight differences in the positions of the atoms. And I think you would spot that quite easily in the Patterson, because because in that case you would see enormous origin peaks at kind of rational positions in the unit cell. So the largest peak in a Patterson map's always at the origin, and if you've got the unit cell correct, and you've got the translational symmetry correct, then you see enormous, you only see those enormous peaks at the corners of the unit cell. But if you've missed translational symmetry, let's say you've doubled the length of the x-axis wrongly, you would see an enormous peak of the same height at a half 0, 0. And I wonder whether that's a way of taking structures that are very similar to one another in terms of translational symmetry and sort of pre-processing them before this. And is that a useful thing?
I'm not sure. So I haven't played with like the actual Patterson functions and how they relate to our stuff, but we have looked into it from a theoretical thing, because we've managed to find a very simple example in one dimension even, where a Patterson function is unable to separate two periodic sets, but ours are, because it stores the correct sort of relative information of distances between points. Right. So with regards to Patterson functions, we're confident that they're sort of stronger as a identifier of a crystal, if you like. But in terms of using it for pre-processing or to help or just for comparisons, I'm actually not sure, because I've never played with them myself. So it could be interesting, certainly.
Right. Okay. Thank you very much.
So thank you. That was excellent, Daniel.
Cheers.